Imagine a world where the horizon itself seems to move. The ground does not merely shake, it ripples under a weight so profound that it defies the structural limits of biological tissue. Out of the prehistoric mist of the Jurassic, a neck rises like a living crane, reaching higher than a four-story building to pluck the topmost needles from a conifer tree. This is the world of the Sauropoda, a lineage of titans that reigned as the undisputed heavyweights of the Earth for over 140 million years. From the recently discovered giants of 2025 to the legendary colossi of the Cretaceous, these were not merely animals, they were biological cathedrals. This is the story of how life achieved the impossible, conquering gravity and engineering the largest hearts, lungs, and bodies to ever walk the dry land. The scientific understanding of sauropods is currently undergoing a massive paradigm shift due to a discovery made in the final months of 2025. In the Sichuan Basin of China, an international team unearthed the remains of a new mamenchisaurid named Tongnanlong zhimingi. This discovery is crucial because it provides the most detailed look yet at the transition between medium-sized herbivores and the true supergiants of the late Jurassic. Tongnanlong reached a staggering length of 28 meters, but its most important contribution is found within the microscopic architecture of its cervical vertebrae. The 2025 analysis revealed that the internal air chambers, the honeycombing of the bone, were far more complex than in earlier species. This allowed for an even lighter neck relative to body size, proving that the evolutionary arms race for longer necks was driven by a sophisticated reduction in bone density. This find confirms that the biological blueprint for gigantism was already perfected millions of years earlier than previously thought, setting the stage for the 90-ton monsters that would follow. To look at a sauropod is to witness a masterpiece of structural engineering that rivals the finest human cathedrals. The core problem for any 90-ton animal is weight. If the bones of a sauropod were solid like those of a modern rhinoceros, the animal would be too heavy to lift its own limbs, let alone walk. The solution evolved by the sauropods was skeletal pneumaticity. The vertebrae of a sauropod were not solid blocks of bone. Instead, they were complex lattices of thin bone walls and cavernous air-filled spaces. This design provided maximum structural strength while reducing the weight of the skeleton by nearly 35%. These air sacs were not just for weight reduction, they were connected directly to the lungs. This meant that the skeleton of a sauropod was part of its respiratory system, creating a body that was effectively a giant, living bellows. This engineering masterstroke allowed for the growth of necks that could exceed 15 meters, enabling the animal to scan a massive feeding area without moving its massive, energy-consuming body. One of the most intense debates in paleontology involves the cardiovascular mechanics of these giants. If a brachiosaurus or a giraffatitan held its head vertically, its heart would have needed to pump blood against gravity to a height of 12 meters. To achieve this through brute force alone, the heart would have required a blood pressure twice that of a modern giraffe and a left ventricle weighing over 1,000 kilograms. Recent 2025 biomechanical simulations suggest a more elegant solution known as the Siphon Effect. This theory proposes that the return flow of venous blood from the head helped pull the arterial blood upward through a vacuum-like effect, drastically reducing the workload on the heart. Additionally, sauropods likely possessed specialized valves and muscular sphincters in their neck arteries to prevent a sudden, fatal surge of blood pressure when they lowered their heads to drink. While the heart remained a massive organ, the sauropod body utilized physics to conquer the crushing demands of gravity. The secret to the sauropods' longevity and size was not their diet, but their lungs. Analysis of the skeletal cavities reveals that sauropods possessed a unidirectional respiratory system, a feature they share with modern birds. Unlike mammals, which breathe in and out through the same tubes, sauropods utilized a series of air sacs that ensured a constant, one-way flow of fresh oxygen through the lungs at all times. This system was the engine that powered their gigantism. It allowed for extremely efficient oxygen exchange, which was vital for fueling a multi-ton metabolism. Furthermore, this air sac network functioned as an internal cooling system. Large animals struggled to shed body heat, and a sauropod faced the constant risk of literally cooking its internal organs. By pumping cool air deep into the cavities of their bones and throughout their torso, sauropods managed to regulate their temperature in the sweltering subtropical climates of the Mesozoic. Sauropods were the ultimate bulk feeders. They did not chew their food. Their heads were proportionally tiny because they lacked the massive jaw muscles and heavy molars required for grinding tough vegetation. Instead, they used their teeth as rakes or combs to strip leaves and needles from branches, swallowing them whole. The true digestion took place within a massive, complex gut. A sauropod's torso was essentially a giant fermentation tank. The plant matter would sit in the stomach for days, broken down by specialized bacteria and potentially aided by gastroliths, smooth stones swallowed by the animal to grind food in the gizzard. This strategy allowed them to consume low-quality vegetation in massive quantities. An adult Argentinosaurus likely consumed over 500 kilograms of food every single day, a constant intake that was necessary to maintain its mountain of muscle and bone. The image of the lonely sauropod in a swamp is a myth long debunked by the study of fossilized footprints, or ichnology. Across the globe, from the Paluxy River in Texas to the coastlines of Spain, we find mega-track sites where dozens of parallel sauropod paths stretch for miles. These tracks reveal a sophisticated social structure. Large footprints are often found on the outer edges of the group, while the smaller tracks of juveniles are clustered safely in the center. This indicates that sauropod herds practiced active protection of their young, moving as a coordinated unit. These herds were nomadic, following seasonal rains and the growth of new forests. The passage of a sauropod herd would have been an ecological event in itself, clearing vast swathes of forest and leaving behind deep craters in the soil that would become temporary ponds for other life forms. The life cycle of a sauropod is a story of explosive growth. They began life in eggs no larger than a soccer ball, yet they reached the weight of a bus within a decade. This growth rate is almost incomprehensible in the animal kingdom. A hatchling titanosaur would increase its mass by over 10,000 times to reach its adult weight. Bone histology reveals that sauropods reached nearly full size in as little as 20 to 30 years. They did not have the slow, decades-long growth of modern cold-blooded reptiles. They grew with the speed of warm-blooded giants. This rapid maturation was a survival necessity. In a world populated by predators like Allosaurus and Carcharodontosaurus, the only true defense for a sauropod was to become too large to be eaten as quickly as possible. Every year spent at a smaller size was a year spent in danger. While their size was their primary defense, many sauropods were equipped with active weaponry. The diplodocids, such as Apatosaurus and Diplodocus, possessed tails that ended in a thin, whip-like structure known as a flagellocaudate. Computer models have shown that if a Diplodocus were to flick its tail, the tip could move at supersonic speeds, exceeding the speed of sound and creating a crack louder than a gunshot. This was likely used for communication and intimidation rather than physical contact, as the tip was too delicate to strike a predator repeatedly. Other sauropods, like Amargasaurus, featured a double row of long, bony spines along the neck, which may have supported a skin sail or acted as a visual deterrent, signaling to any predator that the gentle giant was far from defenseless. While the long-tailed diplodocids and the high-reaching brachiosaurs were the stars of the Jurassic, the Cretaceous belonged to the Titanosauria. These were the final and most successful of the long-necked giants. They evolved a wide-gauge gait, with hips and limbs positioned further apart for greater stability on varied terrain. Titanosaurs were the most widespread of all sauropods, with their remains found on every continent, including Antarctica. Some species, like Saltosaurus, even evolved bony armor plates called osteoderms embedded in their skin to protect against the evolving predators of the late Cretaceous. The titanosaurs pushed the limits of terrestrial biology to its breaking point, with giants like Patagoteton and Argentinosaurus reaching weights of 70 to 90 tons. They were the absolute zenith of the sauropod experiment, thriving until the very moment the world ended. The long-standing debate over whether sauropods were warm-blooded or cold-blooded has been solved by a concept known as Gigantothermy. Because of their sheer volume, a sauropod's body had a very small surface area relative to its mass. This meant that once the animal's body warmed up from the sun and its internal fermentation, it stayed warm for a very long time. Their massive bodies acted as thermal batteries, maintaining a stable, high body temperature without the need for the high-calorie burning required by modern mammals. This allowed them to grow to enormous sizes on a diet of relatively low-quality vegetation. They possessed the stable internal environment of a warm-blooded animal with the low energy requirements of a reptile. This metabolic loophole was the key to their dominance, allowing them to outcompete smaller, more energy-hungry animals for millions of years. Sauropods were not just residents of their environment. They were the primary architects of the Mesozoic world. By consuming hundreds of tons of vegetation, a single herd could prevent forests from becoming too dense, creating open, park-like landscapes. This allowed sunlight to reach the forest floor, promoting the growth of ferns and early flowering plants. Their heavy footsteps crushed the soil, and their massive manure deposits acted as the most significant fertilization system in history, dispersing seeds across vast distances. The world of the dinosaurs was literally shaped by the heavy rhythmic tread of the sauropods. They created the pathways that smaller animals followed and opened the clearings where early mammals took their first evolutionary steps. Without the sauropods, the biodiversity of the Jurassic and Cretaceous would have looked fundamentally different. The journey to 90 tons began in the Triassic period with the humble prosauropods. Animals like Plateosaurus were the first to experiment with the long-necked body plan. These early ancestors were bipedal and significantly smaller, but they possessed the core biological features, the air sac systems, and the fermentation-based digestion that would eventually allow their descendants to conquer the Earth. As the selective pressure for larger size increased, these animals moved from 2 legs to 4. Their bones thickened, their necks elongated, and their digestive tracts expanded. This evolutionary transition from the 10-meter Plateosaurus to the 35-meter Argentinosaurus is one of the most successful lineages in natural history. The prosauropod foundation provided the biological versatility that allowed the sauropods to survive multiple extinction events and changing climates for over 100 million years. The extinction of the sauropods 66 million years ago was a direct result of their specialization. When the asteroid struck and the global food chain collapsed, the animals that required the most resources were the first to disappear. A 90-ton titan simply could not survive in a world where the sun was blocked and the forests were dying. Today, we look at their bones as a challenge to our understanding of the limits of life. They prove that gravity is not an absolute barrier and that life can engineer solutions to the most extreme physical demands. As new technologies in 2025 allow us to peer deeper into their fossilized cells, the sauropods continue to grow in our estimation. They were the monoliths of the Mesozoic, the kings of size, and the ultimate testament to the power of evolution to create the impossible. Sauropods were the true masters of the Mesozoic, biological titans that solved the problems of gravity, respiration, and circulation on a scale that has never been repeated. From the hollowed-out bones of the 2025 Tongnanlong discovery to the 90-ton majesty of the titanosaurs, they represent the absolute zenith of terrestrial life. They were social, intelligent, and physiologically advanced, ruling the planet through a combination of sheer scale and high-efficiency engineering. While the asteroid may have ended their physical reign, their echoes still vibrate through the halls of science. A reminder of a time when giants walked the Earth. If you are ready to continue exploring the deep-dive stories of the most incredible creatures to ever walk the Earth, please consider subscribing to this channel. Your support allows us to continue bringing the latest scientific evidence and the cinematic drama of the prehistoric world to life. Tell us in the comments, which sauropod do you think was the most impressive? The long-necked Diplodocus or the massive Argentinosaurus?